Welcome back, everyone. We're in Chapter 12 in Solutions, and we're now to the second section, 12.2, which is on the terms electrolytes and non-electrolytes. If you see electricity in electrolytes, you understand that it has to do something with charges that are moving, because that's what electricity is. It's electrons coming from the word electron, which is a negative charge that's moving in a wire, say. But you can have electricity in a liquid. You could get shocked if you drop your hairdryer in the bathtub. So why? That's because the water itself can act as a conductor of electricity if that water has something in it that are charged particles. Say any kind of solution that has any kind of solute that is positive or negative, those positives and negatives can move around in the water because it's all free to move. It's in a liquid. So an electrolyte has something to do with a charge that is free to move. A non-electrolyte is something that's not going to break down into charges. So if you have a substance that you dissolve into something else and it breaks apart into charged particles, then you're going to get something that can cause an electric current, and you'll have an electrolyte. If you have something dissolved in something else that it does not break down into charged particles, then you cannot have electricity in that sense of moving charges within some kind of a conductor, say in this case water. Okay, so we're going to see that some substances will break apart into ions, okay, and some completely break apart. So if you were to take a teaspoon of, say, table salt in water, it will completely dissolve. Okay, if you have a lot of water and a little bit of salt, every single one of those eventually, and it gives it a little bit of time, will completely break apart and dissolve. Some things will dissolve instantly, some things will dissolve slowly, but because it's going from the outside of a particle to the inside of, say, a crystal, to where every single one of those sodiums and chlorines eventually will be dissolved. So we're have some definitions, but we're gonna look at ones that completely break apart, some that break apart only partially, and then some that don't break apart, at all. So the ones that break apart completely are called strong electrolytes. Okay. Now a strong, if you've ever heard something strong like that it could do damage or that it's dangerous, strong in this case is just the idea that it completely dissociates. Now I need you to know the word dissociate. Dissociate is this is the word break apart into ions. Okay, if you dissociate a formula unit or dissociate a ionic compound, it will break apart into positive and negative ions, 1 to 1 or 2 to 1 or 2 to 3 or whatever the formula is of those ions. So strong electrolytes completely dissociate in water, and everything at the end is ions. So you have nothing left. If I put sodium chloride in, at the end I have no sodium chloride at all. I only have sodium ions and chlorine ions in water, and there's nothing left. Once I have those dissolved in the water, I've got positives and negatives. If I were to drop my hair dryer, God forbid, into the bathtub, those positives and negatives would be able to move if it can come in contact with the electricity from the wall. Okay, so that is could form an electric current. Weak electrolytes simply don't break down completely. So it would form positives and negatives. So it is made up of ions, but it would break apart incompletely in water. So it doesn't dissolve all the way. So when it dissolves, if you were to dissolve it into the, say, water, you would have mostly molecules, okay, rather than all ions. Okay, so you're going to have a few ions because there's a little bit of electrolytes there, but you're not going to have a strong electrolyte that would go completely into ions. And so since there's only a little bit of positives and negatives, say in this water, it would conduct a weak current. So if you put a light bulb, say, in with, and connected, and it went into this, to where you're actually using the water as part of the circuit, you would get a very weak glow to the light bulb. Whereas if you put the light bulb in, a conducting light bulb through a liquid that you're using as part of that circuit, and it was a strong electrolyte, you would have electricity would go through it easily, and you would have a bright light bulb. Okay, so it's a weak current. The other option would be that it doesn't break apart into positives and negatives at all. So if you were to put sugar in water, it doesn't break down. It's not ionic. C6H12O6, that's all on the upper stair step of on the periodic table. Those are all nonmetals. They do not form ions. They all are covalently bonded together, and water doesn't do anything to them. Now, it looks like the water can dissolve sugar, but it's actually not dissolving the same way that, say, salt is, where it's breaking it completely apart. Okay, it is solvated. You can solvate a sugar molecule slightly because of the hydrogen bonding. There's oxygens and hydrogens in sugar, and the water can surround it a little bit, but it's not breaking that apart. Every one of the insides of those little pods of water are complete sugar molecules. So it's not really it's dissolving inside the water, but it's not dissociating. It's not breaking it, shattering it, and breaking it apart like salt would be. So a non-electrolyte is all molecules. There are no ions, and there would be no electric current at all. If you were to dissolve sugar in water and put a conducting light bulb in attached to a battery, you would get no glow at all. Okay, it's a non-electrolyte. Okay, it only produces molecules. So a non-electrolyte here, this is sucrose, so this is sugar. So it does dissolve. You can see on the right that the water molecules are hydrating them because sugar is C6H12O6. So it's got H, that's hydrogen bonding. You have oxygen, that's hydrogen bonding. So the H's in the water and the oxygens in the water do attract to the particles in that sugar, but it doesn't rip it apart. It dissolves it, but it does not dissociate it. It doesn't rip it into ions. Since there are no ions, there is no electricity. So here's some examples. Strong electrolytes completely dissociate. And you should know by now that dissociation is breaking apart into positives and negatives. It all goes completely to ions, and since there's ions in the water that can move, you've got electricity. You've got moving charges, and that's what electricity is. Lots of examples. You've got all of these hydroxides. You've got all of these group 1 hydrides, or group 1 halides, like halogens. So lithium and fluorine and potassium and bromine and all these group 1, group 7 kind of combinations, they break down beautifully. Lots of hydroxides break down beautifully. We'll talk about examples later. Weak electrolytes are ones that break down a little bit, but mostly they're going to show up as molecules. They're only going to have a little bit of ions there, and so you have a weak conduction of electricity. So weak acids do this, like acetic acid, so that's hydrogen plus acetate. It doesn't all break down. So you're going to have some hydrogen acetate or acetic acid that stays acetic acid, and then a little bit of it's going to give away its hydrogen. You're going to have acetate and hydrogen. So you're going to have a little bit of ions, but not complete. So that's a weak electrolyte. And then non-electrolytes, alcohols don't break down, sugars don't break down, anything usually organic, lots of covalent bonds are not going to break down at all. Okay, I hope that helps you, and I'll see you in class.